This problem is related to complex formation and solubility. Question says, use values of Ksp for AgI and Kf for AgCN2 minus to calculate the molar solubility of AgI in pure water. Part B says, calculate the equilibrium constant for the reaction. Part C, determine the molar solubility of AgI in 0.1 m NaCN solution. So let us discuss part A first. That is, we have to calculate molar solubility of AgI in pure water. So we will write dissociation for AgI. AgI will dissociate and it will give Ag plus I minus, and solubility product for this is given, that is 8.3 into 10 to the power minus 17. Now let us say x mole of per liter Ag plus dissolves, then I minus will also be x mole per liter. We can write expression for Ksp. So Ksp will be concentration of Ag plus multiplied by concentration of I minus. Now concentration of Ag plus is x, concentration of I minus is also x. So this is x into x, this is x square. X square is equals to Ksp. So from here we can write x is equals to under root Ksp. Ksp value is given at 0.3 into 10 to the power minus 17. So we can write 83 into 10 to the power minus 9. So under root of 83 is 9.11. So x is 9.11 into 10 to the power minus 9 m. So molar solubility of AgI in 1 liter solution is 9.11 into 10 to the power minus 9 m. So molar solubility of AgI in pure water, this will be 9.11 into 10 to the power minus 9 mole per liter. Now let us say part B. We have to calculate equilibrium constant for this reaction AgI solid plus 2Cn minus. This gives AgCN2 minus equals plus I minus. AgI solid plus 2Cn minus, and this gives AgCN2 minus plus I minus. So we have to calculate equilibrium constant for this reaction. Now we can write two equations and then sum. AgI solid dissolves and it gives Ag plus I minus. Equilibrium constant for this reaction is Ksp. Now next we can write a formation expression, that is Ag plus can combine with 2Cn minus to give AgCN2 minus, and equilibrium constant for this equation is formation constant Kf. Now Ag plus, that is coming from the first equation, that is solubility, is used in the second equation, that is formation of a complex. In that case we can add these two equations. So Ag plus formed is same as Ag plus used. So we can add these two equations to get the overall equation. So in that case we will have overall equation is AZI plus 2Cn minus, and these are aqueous. AGI is solid, 2Cn minus aqueous, and this will give AgCN2 minus aqueous plus I minus aqueous. Let us say equilibrium constant for this reaction is K dash. Then if I sum two equations, equilibrium constant gets multiplied, so this is KSP into KF. So K dash is equals to KSP into KF. KSP is given at 0.3 into 10 to the power minus 17. So this value is KSP. Similarly, KF is also given. KF is 1 into 10 to the power 21. So K dash for this reaction will be at 0.3 into 10 to the power 4. So this equation will have a equilibrium constant of 8.3 into 10 to the power 4. Now C part says calculate the molar solubility of AgI in 0.1 m NaCN. So this time we have to calculate solubility of AgI in 0.1 m NaCN. 0.1 m NaCN will give Na plus of 0.1 m and Cn minus of 0.1 m. Because this is a strong electrolyte, so it will dissociate 100%. NaCN is a strong electrolyte. Now what will happen in the presence of Cn minus? First AgI will dissolve and dissociate to give Ag plus plus I minus. Now there are two ways to increase the solubility of AgI. Either we remove Ag plus or we remove I minus. If I remove Ag plus, this equilibrium will shift right side, so more Ag will dissolve, more AgI will dissolve in this solution. To remove AgI, we can form a complex. That is Ag plus can combine with 2Cn minus and it will form a complex. In that case Ag plus gets utilized and reaction will proceed in the forward direction. So if I add these two reactions, that is Ag plus used is same as Ag plus produced, so we can write AgI plus 2Cn minus. This will give AgCN2 minus plus I minus. And we have calculated equilibrium constant for this reaction, that is 8.3. So let us check here, 8.3 into 10 to the power 4. Now at t is equals to 0, we have been given initial Cn minus is 0.1. So Cn minus is 0.1 m and there is no AgCN2, there is no Ag minus, I minus. Now since the equilibrium constant of this reaction is very high, so this reaction will go mainly towards the right side. The meaning is whatever we have Cn minus, that will be utilized. So we can assume t is equals to t, that is equilibrium time. Approximately there is very small concentration of Cn minus, that is approximately equals to 0. That is all the Cn minus gets utilized. Now 2 mole of Cn minus gives 1 mole of AgCN2 minus. So 0.1 mole will give 0.05 m. Similarly 2 mole of Cn minus will give 1 mole of I minus. So 0.1 mole will give 0.05 mole per liter. So in this case we are using molar ratio. So 2 mole Cn minus give 1 mole of AgCN2 minus. So 0.1 will give 0.1 by 2, that is 0.05. Now see, concentration of I minus is same as solubility. So whatever AgI dissolves, it will give Ag plus and I minus. Now concentration of I minus is same as solubility. Because I minus is not utilized anywhere, so concentration of I minus is same as solubility. So in this case solubility is 0.05. So now see, solubility in the presence of NaCN is 0.05 m, but in case of solubility pure water, this solubility is 10 to the power minus 9 m. So solubility has increased with a large amount. So in case of complex ion formation, solubility increases. Now one can also calculate concentration of Cn minus. This is exactly not 0, but we can calculate Cn minus concentration. Let us write expression for K dash. This is concentration of I minus into concentration of AgCN2 minus this divided by concentration of Cn minus raised to the power 2. So concentration of Cn minus raised to the power 2. Equilibrium constant is 8.3 into 10 to the power 4. Now concentration of I minus is known 0.05 and concentration of AgCN2 is also 0.05. This divided by Cn minus raised to the power 2. So from here we can calculate Cn minus. This is 0.05 into 0.05 divided by 8.3 into 10 raised to the power 4 and under root. So concentration of Cn minus is equals to a square root of 0.05 into 0.05, and this divided by 8.3 into 10 to the power 4. So this value is 1.73 into 10 to the power minus 4. So Cn minus is very small, that is 10 to the power minus 4. So we can assume initially we have 0.1 and finally we have 10 to the power minus 4. So we can assume finally concentration of Cn minus is approximately equals to 0. So concentration of Cn minus is very small, and this assumption is valid. Because concentration of Cn minus is very small number, 10 to the power minus 4. So you see, this problem is related to how we increase solubility. One way to increase the solubility is we can remove anionic part, and another way to remove is cationic part. Cationic part can be removed by formation of complex ion. So if complex ion is formed, solubility will increase.